So this talks about force and neural activation of muscle. The central theme is how does the nervous system control muscle force? So what we want to start with in this class is the basic element of force production from the perspective of the nervous system. And what we see in this slide in the upper right-hand corner is a picture of branches of an alpha motor neuron and their connections to various myofibrils within a muscle. Remembering that a myofibril is a cell and houses the myofilaments that generate force. We can see that one alpha motor neuron branches and innervates several, in this case 1, 2, 3, 4, 5 myofibrils. And that's exactly how the nervous system is organized, with each alpha motor neuron exiting out the ventral root, branching and innervating a different collection of myofibrils. The collection of myofibrils and the alpha motor neuron are together make up a single motor unit. And the smallest unit of force production from the perspective of the nervous system is a motor unit. There's some rules about motor units. One is that the number of myofibrils that a motor unit innervates can vary. And essentially, smaller collections of myofibrils or muscle cells means that there's finer control. In other words, there's smaller steps in force output. Larger collections of myofibrils connected to an alpha motor neuron means that there's bigger steps in the force output, meaning that it's less fine control. So in the hand, for example, you'd expect to find motor units that have fewer myofibrils, and in the back muscles that have gross control for posture and things like that, you might have motor units with large numbers of myofibrils because they don't need as fine a control. There's other activation principles that are important that, for example, the type of alpha motor neuron is associated with specific muscle fiber types. So a smaller diameter alpha motor neurons typically innervate type 1 motor units, which are activated more frequently. In large diameter alpha motor neurons innervate type 2 motor units, which are activated less frequently but generate higher force. So use is associated with muscle fiber type, essentially. And so the question becomes, is it possible to activate a single muscle fiber? And the answer is no, because the smallest unit of force activation by the nervous system is an alpha motor neuron. So if we're trying to understand how the nervous system regulates or modulates force development of muscle, what we're really focusing on is recruitment of motor units, and how fast, once one is recruited, is how fast it's activated. So we want to talk about those two things, and we're going to call them one, recruitment, where additional alpha motor units are recruited, and then rate coding, which is the other alternative where you recruit one at a faster rate. So we'll start with rate coding, and essentially we want to focus on, in this graph to the right, we see the top graph is the force output on the Y, and then the stimulation rate on the X. And so as we kind of go to the right, we have increasing rates. And so what we can see in these graphs here, let's focus on the middle graph B, and we can look at a 5 hertz rate, which is 5 stimuli per second, a 10 hertz rate, and this 20 and 30 hertz rate. And essentially what we can see is that at the 5 hertz rate, there's a depolarization here. There's some force developed before that motor unit has time to completely go back to zero and have no force. There's another stimulation, and we can see that it gets another depolarization and another and another and another. And so essentially there's not much at 5 hertz. There's not much augmentation in force or enhancement in force. It's about the same. And so if we kind of notice, once we go to 10 hertz, look what happens to the force production. It's the same myofibril, and it's the same number of sarcomeres that are being involved in the contraction, but the nervous system takes advantage of contracting the cell repeatedly, and by doing that, it establishes higher number of cross-bridge formation and then can augment the force output. So from going from 5 to 10 hertz, note that the force output of a motor unit is more than doubled. And so the number of cross-bridge formations that are being formed is higher. Now, so from 5 to 10 hertz, there's a big augmentation of force output by increasing the rate of depolarization or of activation of the muscle. But then when we go from 10 to 20 hertz, the improvement there by going even faster slows down. And then once we get to 30, we're basically maximize the amount of rate coding that we can take advantage of. So we can't really enhance the amount of cross-bridge formation any further. And so that's kind of what this graph indicates, and you'll talk a lot more about this in neuroscience, but essentially around 30 to 40 hertz is the peak amount of force augmentation you can get. Above that, you don't usually get increasing amounts of force output. So the other alternative is to recruit other motor units. And so we have here is a kind of an EMG record. So essentially we're stimulating an alpha motor neuron on this top line. And we can see this is an upside down M, so the M is pointed down in this case. Here's a right side up M. So this is a motor unit that depolarized when the person started to just barely contract their muscle, just enough that they needed one single motor unit to contract. And we can see that essentially here's another motor unit and this one. So we see here's one motor unit. It's fairly close to the recording device, so it has a big amplitude. This motor unit's kind of far away, so it has a smaller amplitude. So actually we have two motor units here. So there's 1, 2, and so we're just getting these two motor units. And look at the rate, because we can imagine times on the x-axis here. So we see it's like, contract, 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 contract. And so it's a fairly slow rate, but the muscles recruiting two motor units equally spaced apart in the terms of the timing of their contraction. Now here we see on the bottom graph, we see 3 motor units. So you can kind of look at their patterns. So here's one here, 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 here. We have another characteristic one here, 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 and now there's a third one here, 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 and here. So essentially the person started out here with recruiting 2 motor units, and then decided they needed more force for the activity, and then recruited 3 motor units. So we'll actually try to look at this in the laboratory by taking a single and indwelling motor unit recording. So this is another way to look at force output as we recruit different motor units, and this kind of integrates recruitment of different motor units with muscle rate coding. So the MU1 is motor unit 1, and then 2, motor unit 3, motor unit 4. And we have muscle tension here on the Y, and then time on the X. So let's say we activated motor unit 1, and so it was able to produce the tension here shown on the dotted line, and we had each one of these dots signifies a depolarization. So there we had a depolarization, contracted, contracted, contracted. So it's fast enough to create a smooth kind of high, so we are getting this around 40 hertz high force development. So there we've maximized the rate coding, and now we need to ramp up the force even more because our goal is to get up to this point here to handle the external load. So we recruit motor unit 2, and so we recruit motor unit 2, and then we rate code it up to its high end 20 to 30 hertz range, and then so now we have that. So now we have muscle 1 and motor unit 1 and motor unit 2 both contracting, giving us a force that is approximately half our goal. And then we have to do the same thing. We add the recruit, the third motor unit, and then the fourth motor unit. And we've basically combined recruitment and rate coding here to modulate force and hit our target goal of this theoretical point on the muscle tension graph. So essentially, the combination of rate coding and recruitment represents neural drive to the muscle, and we measure that using electromyography. So electromyography is a signal of muscle excitation that is easily obtained from either surface or indwelling electrodes. Surface sensors are placed on the skin. They are bipolar, and they record the amount of electrical activity under the muscle. And then indwelling electrodes are insulated wires that are inserted into the skin with a needle. It's usually small gauge, and then the needle's extracted, and then the wires are left in the muscle and then connected up to a recording unit to record the differences in electrical potential in the muscle. There are some advantages of the indwelling electrode, and the major advantage is it records specifically from the muscle it's in, where surface electrodes, because they're on the surface, they can pick up other muscles and electrical signals, such as from your heart. So what's an EMG signal look like? And so this, if we look to the right, we can see that we have a graph where voltage is on the y-axis, and then time is on the x-axis here. And we can just see these kind of blue bursts of activity. And basically the signal itself is a function of how the electrodes are set up, and basically they measure the difference between two reference points, and that in essence gives us a differential signal, which means that basically it's recording an equal amount of positive and negative voltages. So what we're really interested in is just how much activity there is in general when we look at the EMG, and that total amount of activity is really captured here in this number 1 point. It says raw EMG signals equals the total neural drive, which is the sum of the rate coding and recruitment that occurred during the movement. So it's the amount of depolarizations, the total number of depolarizations that are necessary to either rate code a single muscle fiber or rate code and recruit other muscle fibers as well. So this kind of signal gives us an idea of how hard the nervous system is driving the muscle to try to produce force. And so it's not surprising to us that we get this kind of arbitrary signal that has positive and negative values. So it's more kind of valuable to us at times is to have something we call the rectified EMG signal. So because the EMG signal, the way we process it and collect it, it sums to zero, what we want to do, the negatives are equally as important to us as the positives because they both indicate the neural drive to the muscle. So if we just take the absolute value, which is the same thing as rectifying the signal, what we get is we just convert all the negative values on this top graph to positive. We get an outline of the neural activity that looks like this. So the area under this particular impulse would indicate the amount of neural drive from the brain that was transmitted to the muscle to create force to meet the external load that muscle was being applied at that joint, and that muscle needed to produce to have the movement occur the way that it did. And each one of these impulses represents the same kind of neural drive. So we can see that EMG gives us an insight into how the brain is trying to drive the muscle or stimulate it for muscle control, for muscle force modulation. Okay, so now we kind of have a basic understanding of what the EMG signal is telling us, and we understand it's both rate coding and recruitment, and it's trying to modulate muscle force, or it is modulating muscle force to meet an external load. So the next question we could ask is, how do we interpret differences in the EMG signals? So the first situation or scenario we're going to consider is an isometric contraction at two different joint angles. So we have an example here. We have a dorsiflexed joint, okay, and so we're recording from the gastroc muscle. So we have the ultrasound reading that we can see here of where the gastroc muscle meets the Achilles tendon, and we see the theoretical muscle length here in LM, and then we kind of compare that to a plantar flex position where we see the muscle length has been shortened. Okay, so if we think for a minute about the necessary, and we have one other thing to kind of understand the experiment, that in both conditions, so when the ankle's dorsiflexed or when the ankle's plantar flexed, the external load remains identical. So if that's true, then if the external load is the same, the moment arms, taking into account that in this case they're probably fairly similar, that in essence the muscle force would have to be fairly constant in both of these situations. So given that, what we would say is that the amount of neural drive to the muscle is dependent on muscle length. So for example, when the muscle's in a more toward resting length or this kind of minimal dorsiflex position, what we would suggest is that the EMG is kind of moderate. And so here we have the positive and negative voltages, 0, and we have this activation that indicates the depolarization necessary to maintain force in the muscle to meet the external load. But in the second example, where the ankle's plantar flex, now we've significantly shortened the muscle. So that significant shortening means that we will be operating on a different limb of the force length curve, and so those muscle fibers or myofibrils that house the sarcomeres will be shortened more than they were when the ankle was dorsiflexed. So in order to produce the same amount of force and meet the external load, we have to increase the EMG activity. So in this case, the differences in length would explain the differences in neural drive. So neural drive is essentially indicating how much the nervous system is driving the muscle to meet force demands, and other factors like length are helping determine how much actual force the muscle is producing given that neural drive. Another example is the force velocity curve. So in this case, we have the force velocity curve here to the right, and we can see some different arrows pointing here. But just to review the curve one more time, we have the y-axis here, which is muscle force. We have contraction velocity, which is on the x. 0 indicates an isometric contraction and is labeled so here. And negatives are eccentric and positives are concentric. So let's assume that to meet an external demand at the ankle, we need to produce somewhere around 35 newtons of force, or here, and that's represented here in this red line. And we'd like to be able to do that at different velocities. So essentially, the first thing we can note is that to produce that much force at 0 velocity, that's about 50% of the peak force, isometric force, that this person can produce. So it's about half of their total capacity for that particular external load. Now, if we second consider the max velocity that we can produce that particular load, we could go to the right. We can see that essentially it's about 25% of the muscle's peak velocity. At that point, we can no longer produce a 40 Newton or 50% isometric load, and so essentially we can't meet the demands anymore. And so if we were to try to continue, we would fail at speeds faster than 25% of the contraction velocity. So then we could also consider what the neural drive would be in order to hit a speed of about half, this peak velocity of around 30%. If we're at 15 here, well, now we're kind of in between those 2 points. And so for right here, it takes about 75% of the muscle's capacity to hit that particular, to maintain this force at a speed of 15% of the muscle's contraction velocity. So essentially what we can see is that neural drive varies with contraction velocity when force is kept the same. So essentially at 0 speed, we only need about 50% neural drive to the muscle. At a speed of 15% of the peak contraction velocity, we would need about 75% of neural drive to the muscle. And then at 30% contraction velocity, we need all the neural drive. We need maximum neural drive because it's the maximum muscle's peak muscle output capacity that we need to meet that particular load at that speed. Okay, and so we're starting to understand is that neural drive varies with contraction velocity. So in summary, this particular slide and picture would be a good one to study and reflect on. Essentially what we're doing here is modeling the different mechanical design features of the muscle, tendon forces, and the different variables we've been identifying that influence force production of a muscle. And so we can see first is this, the CE stands for contractile element, the PE stands for the passive element, the SE stands for the series elastic element, and that is the tendon that transmits the muscle force to bone. And that the end effect of all this is to draw the two bones together, so creating muscle tension. So essentially we're most interested in the contractile element, and we know that the contractile element's influenced 1 by force length, 2 by force velocity, and now we also know that the amount of neural drive is partially dependent on what the force velocity is and what the force length is. So for a different neural drive and force velocity, for a different force length and force velocity, we might need a different neural drive. And then the amount of tension that gets developed and transmitted to bone is partially attenuated by the minimal but important level of a spring constant of the tendon. So let's give a couple clinical examples that apply these principles to practice. The first is something called a stretch shortening cycle. And one of the things that's going to be evident as we go through the class is that stretch shortening cycles are a common way for people to move. And there could be an important energy conservation reason for people to use stretch shortening cycles. So essentially this shows a typical stretch shortening cycle where just before a joint is stretched or a muscle stretched or elongated across a joint, it's pre-activated. So in this case, as somebody's starting to land on the ground, just a few milliseconds before they land, the muscle's activated so that when it lands, okay, in this case on the toes, as the muscle's lengthening, it's eccentrically contracting. And then without a pause, and that's an important factor, is that there's no pause. If that stretch or eccentric contraction is immediately followed by a concentric contraction, that's called a stretch shortening cycle. So basically it's pre-activation followed by a stretch with load, and that's followed immediately by a shortening. So this is an example of a research study that examined stretch shortening cycles. And we can see this is a researcher here, Dr. Comey, and he has a needle and he's weaving a fiber optic cable through the Achilles tendon. And superiorly on the calf, we can see here, these are EMG electrodes. They're going to simultaneously record from the muscle to give him the neural activation and the force output of the muscle. So by doing this, he can then look at how neural drive affects force length and force velocity relationships. And we can see over here to the right his data. So we have EMG activations, and these, of course, are rectified signals that tell him about the neural drive. This is to the anterior tib. This is to the medial gastroc muscle, which is one of the calf muscles, and the soleus muscle, which is the deeper calf muscle. And then he also was able to obtain the length of the muscle itself. That's what's being recorded here. And then here's the force from the fiber optic cable. So essentially he has force and information about length, and then he can also differentiate length and get velocity. So he's able to connect the shortening, the actual shortening velocities and force output in a muscle in vivo as somebody's moving. So we want to focus our attention on the hopping task here to the right, and then we can see that the velocities are here on the x-axis, very similar to the force velocity curves that we were studying before. We have negative eccentric velocities to the left and positive concentric velocities to the right. And then we have tension or force production here on the y-axis. So the start of the movement was focused on the dark black line. We can see there's very little force developed as the person's approaching the ground. But then as they hit the ground, they rapidly develop eccentric force. And as their heel hits the ground, they move toward a zero force or isometric contraction. And then here's what's surprising. So as we go in toward now a concentric contraction, watch what happens. The force graph from the fiber optic cable circles out here and then kind of drops down as the person accelerates into plantar flexion. So what Dr. Comey's done here is plotted a theoretical force velocity curve for this particular muscle. And what we notice is that the muscle, the actual force output exceeds that of what we would normally expect from the force velocity curve. And so what that means is that the contractile element it was at its maximum capacity at this point where the cursor is. But instead of dropping down onto the force velocity curve, it continued to produce increased force despite moving at velocities where it really couldn't produce that much output. So the answer becomes, in terms of like, does this mean that the contractile element calculations we're making were incorrect? In other words, the muscle contractile element can actually produce more force, and the answer is no. The answer here lies in the tendon dynamics. And so remember that we said that the tendon is a spring. And so because the tendon became stretched here on the eccentric side, what we're seeing here is the effect of the returned energy of the rubber band or stretchiness of the tendon. So basically, immediately after the tendon was stretched, we had a very brief isometric contraction that immediately moved into a concentric contraction. What this is indicating is that the muscle is able to take advantage of the stretchiness of the tendon by recapitalizing on the force and the shortening of the tendon that augments the muscle force output enough that it enhances the movement. And so essentially this shaded area is the amount of augmented force production that was produced by the elastic recoil of the tendon during the concentric phase of this stretch shortening cycle. So what will turn out to be true is that stretch shortening cycles are an important mechanism of efficiency or decreasing the need for ATP in all kinds of movements like walking and pitching. Okay, so this is another example of integrating elements from the research, the muscle design lecture, and neural activation. So after some patients who have ACL injuries, which is a very powerful ligament in the knee, decide to live with instability for some period of time. And what this MRI is showing us is the difference between uninjured and injured ACL groups. And we want to focus here is on the non-Koper or the the group that experienced some amount of muscle atrophy. So here's the injured, non-injured side cross-section. We can see that the muscle girths here are fairly strong. And then in comparison on the right side, we can notice that the muscle girth is less and that the cross-sectional area is lower. And we know from a cross-sectional area is connected at least somewhat to physiologic cross-sectional area. And so what we would expect is that the activation of this muscle would produce less force overall. And so what we can see here is the MRI readings. This is the hamstrings and quadricep muscles. The hamstrings would be down here, and then the quadriceps are up here. We can see is that this bar graph right here represents the amount of atrophy that we see in the quadricep muscle. And we can see that the black here is representative of the ACL deficient knee, which is significantly less than the non-injured knee. So essentially there's definitely atrophy in the muscle. Now, interestingly, when they tried to correlate atrophy, just the amount of cross-sectional area with muscle force output, the correlation was weak. And so it was only when they combined a measure of the atrophy or mechanical state of the number of muscle fibers in parallel or myofilaments in parallel that's reflected in cross-sectional area measurements with when they included a neural component, like how much neural drive there was to the muscle. So in other words, the person's ability to fully activate the muscle, when they combined the ability of the person to fully activate the muscle with the amount of atrophy, then they had a very good correlation with the amount of isometric torque that the person could develop. But prior to adding activation, the correlation was quite weak, meaning that not only did the muscle atrophy kind of vary between subjects, the amount or the ability of the person to really access their nervous system and drive the muscle with their nervous system was also activated. So only through combining activation and the muscle state itself were they able to establish a strong connection between the isometric torque, which is connected to the force output in this particular case, with the muscle state. So what this underscores is the importance of both activation and things like muscle design when you're considering muscle function in your patients.